So, hello everyone. We are recording this lecture on cryptographic system categories, and in this video, we are going to learn about what are cryptographic systems, and we have actually done a brief overview of what are crypto systems in our previous videos as well as in the class. So we are going to cover some of the categories here. We will see some of the examples of those categories, which is a very short video about what are the categories of cryptographic systems. So let's begin with the first definitions or differentiation of the categories. So if we go by the first thing, that is what are the types of categories, we can categorize the cryptographic systems in the following types. The first is the type of operations that are used for transformations. So what are operations we apply on converting a ciphertext or a plain text to a ciphertext and ciphertext to a plain text. So these are known as operations. So we can have two type of operations that actually are used for transforming a plain text to a ciphertext and a ciphertext back to a plain text. It is known as substitution, and one is called as transposition. We will see the definition as well as the examples in the upcoming slides. The next is a number of keys that will be used in the operations in transformation of or substitution. So if we are using it can be a symmetric key or an asymmetric key. And we have discussed the symmetric and asymmetric keys, what are they, and how we actually use them. Uh, but we will again see it in this slide. The third definition is difference is the category. The third category is the way a plain text is processed. Maybe it can be processed in a form of a block cipher, or it can be in form of stream, because it's a stream cipher. Okay, so these are the basic three categories of cryptographic system. So now going ahead with one by one each type of these categories. So the first thing is transformation. The first type of transformation that we want to discuss is called substitution. In substitution, we replay each element by another. We not replay, it's replace. We replace each element by another element. So it say that we will try to change one element by a different element. Okay, if we have a, we can replace it with z. If we have a x, we can replace it by c, suppose. So we actually replace each element by another element. So this replacement can be monoalphabetic or it can be a polyalphabetic in nature. If the replacement is one to one, so if we change one element to another one and to the same element, we call it as a monoalphabetic. And if it is one to many, it is known as polyalphabetic in nature. So just understand that when we have one to one replacement, it is known as monoalphabetic. When it's one to many replacement, it is known as polyalphabetic replacement or substitution. So the example of monoalphabetic and polyalphabetic transformations is shown here. So if the plain text is hello and the corresponding ciphertext is who. So what we have done here is we have changed the H to K, E to H. Both the L's are mapped to the same word called O, right? And O is mapped to the word called R. So if you go and check, if you create a table with A corresponds to 0 and Z, and B corresponds to 1, C corresponds to 2, and likewise Z corresponds to 25, you will see that when we transform S to K, we shift by 3 alphabets. Okay. Likewise, when we move from E to H, we again shift that particular system by 3 alphabets. L to O again have a 3 shift toward the right, and O to R again have a shift of 3 towards the right. So we can say that monoalphabetic particular transformation actually maps each element to the same element which is mapped to overall system. So whenever we are having a L in our text, plain text, it will map to O, right? Wherever we'll find this L, we will map it to the word called alphabet called O. Wherever we have a alphabet called O, we will map it to R. Wherever we have a word called alphabet called H, it will map to the alphabet called K. So it is one-to-one mapping. So on the other hand, if again we have a plain text called hello and the corresponding cipher text is K, G, W, J, R, we see that H is mapped to K, E is mapped to G, one L, the first L is mapped to W and the second L is mapped to J, and O is mapped to R. So you see that the first L is mapped to W and the next L is mapped to J. So you are having same input word alphabet mapped to two different output alphabets. So it's one to many mapping. Okay. So earlier one was one to one mapping. This is one to many mapping. So each element of the plain text was shifted by some to some elements the right or the left. However, the shift is not predetermined. So converting back polyalphabetic to a plain text is particularly challenging if you don't know the keys. Okay, but on the other hand, if you know the frequency distribution of the words and you know that they are following monoalphabetic transformations, it's pretty easy for you to map it back to the original words. Okay. So this is the difference between the monoalphabetic and the polyalphabetic transformations. Now the second thing is called transpositions. So transpositions, we do not substitute each element, instead we rearrange them. So what we do is in this we don't substitute a new element in place of a plain text. Okay, what we do, we have a plain text, we just rearrange the letters or the alphabets in that plain text to create a new cipher text. So suppose the plain text was hello, the cipher text can be leholo. Okay, so LELHO. So what we do, we rearrange that plain text into some different text which maybe may we have a meaning or may not have a meaning. Okay, but it should be remembered at this point that the plain text and the cipher text that we have shown here, they are very trivial in nature. An actual transposition doesn't have such mappings or such rearrangement. What we do, we rearrange that particular word or a plain text using multiple transformations. Rearrangements are there, but the number of rounds are not fixed. So you change it many times so that you cannot get the original text after 12 or 13 rounds of transformations. Okay. The next thing is the keys. Cryptographic systems can also be categorized based on the number of keys. The keys can be symmetric key or asymmetric key. When both the parties, the sender and the receiver, use the same key, it is known as symmetric key system. Generally, we denote a symmetric key by the symbol K with a subscript called S, right? Single key or a secret key is also the names that are given to symmetric key systems. And asymmetric keys, when the sender and the receiver of the information uses the different keys to encrypt and decrypt the information, it is known as the asymmetric key based system. Digital signature scheme, the DSS and an RSA uses asymmetric key based system. Now, the plain text processing may be in form of block or in form of a stream. When in block cipher based approach, we convert the plain text into a square matrix of n cross n dimensions. It is then combined with a key matrix of the same dimension to create a cipher text of the same dimension. So if we have given an example here that we are having a plain text, we have converted the plain text into a 2 cross 2 matrix, and we have a key again in 2 on 2 matrix. When we multiply a 2 cross 2 with a 2 cross 2 matrix, we will get a 2 cross 2 cipher text matrix. Okay, So this is the overall idea of a particular block cipher. What it does, if we have a particular paragraph, so what we decided that we will go with two or two by two matrix. So we have to crop the initial part such that it takes a number of elements that can be put in into a 2 or 2 matrix. Okay, then we have a key, we'll combine that key with that matrix and create a ciphertext. Then we again move to a next set of words, take the new set of data, place into this plain text matrix, convert into ciphertext, then again move ahead, we take the new set of data, put it into the plain text and create a ciphertext. This is how we do block by block. In comparison to stream ciphers, in stream cipher based approach, we convert one element at a time into ciphertext based on the substitution or transformation. We take one element, transform it into ciphertext, then to take the second element. This is like stream of data coming, one by one the data is coming and we are transforming it on the fly. Okay, we are not taking into a block, we are taking in form of stream. But in this lecture, in this course, we are limiting our discussion to block ciphers and to DES based approach. We are not going to discuss about anything about stream cipher, STREAM. We have a spelling mistake here. It's stream, STREAM, stream ciphers. And we are not going to work with stream ciphers in this course. So, now the symmetric cipher model. Symmetric cipher model actually tells you about the Kerchoff principle. Okay, so it's talk about this principle. It says this principle is very important, and it says that the first thing is always assume that the advisory knows the algorithm. That advisory may be the intruder, maybe a person who wants to harm you in the adverse way. So the advisory always knows the algorithm. Secondly, resistance of cipher to attack must be based only on the secrecy of the keys. So you need to always bother about the secrecy of the key that is going to be used. So a simple model is shown here in which there are two people. So one is called Alice and another is called Bob. Alice wants to send a message called hello class. It is a plain text. What she does is she will just put it into an encryption algorithm. The algorithm will change using the secret key, which is we use KS here. The symbol says KS, so the KS corresponds to the symmetric key system. So they will change it into a text which is known as cipher text. It is a text which is not readable or not understandable by anyone. Now the system passes through the insecure channel. It reaches the other end where the ciphertext is again decrypted using the same set of keys, and now the user Bob can see this plain text in form of hello class. So this is a basic model for encryption and decryption. The thing that we want to highlight here is this encryption and decryption algorithms. Okay, the encryption and decryption algorithms are known to every user. Okay, how we're encrypting, how we're decrypting. We may be using RSA, we may be using any other hashing, we may be using any other option. So these are known. The only thing we need to make sure is these keys. Okay, so secure key exchange is the main concern, okay, of Kerchoff's principle, that how you are going to keep the secrecy of the key when you are going to because larger the key, the more difficult it is for anyone to guess the key and to break the code. Okay, even if we know the algorithm, he doesn't know the key, he cannot break the algorithm. Okay, so now coming up to one of the questions, it says a number of keys that are used, because we are talking about symmetric key model, so we are going to talk about symmetric key. So if we are having two parties A and B, so number of keys required is 1, because both the parties agreed upon the single key. Okay, when we have three parties involved, then we should have one key for A and B, one key for A and C, and one key for B and C. Okay, so when we have three parties involved, we need 3 keys. Likewise, when we have 4 parties, we need 6 keys. So if we go on increasing the number of nodes, what are the requirement for n number of keys? So we will ask this question in the class. On the next class, we will tell you what are the number of keys. But as of now, you all should just put up your answers in the comment box of this video lecture, saying what can be the general formula for finding out number of keys required for an n node system. Suppose you are going to put routers out there in a campus. There are n routers, and all these routers has to communicate using a secret key. Okay, but they have one key between both the routers. Okay, so if I have n routers, how many keys will be required? So this is the question. Okay, so we will see your comments, and we see how many of you responds back to this comment, this particular course.